Alright, thanks for watching and welcome to this cool linear algebra and analysis special. Just to show you that you can indeed use linear algebra, which you think of algebra, to study analysis. And the cool thing is, at the same time, I want to show you that the Dirac Delta is not a function, but a distribution. So this is really cool. And as I said, I want to give you this nice application of linear algebra and analysis. In particular, I want to show you how dual spaces are really cool in analysis. So remember, and if you don't know that, watch my videos. So the dual space of V is just the set of linear transformations for a vector space to, let's say, a field, which here assume everything is real valued. So everything is good. Not that complex numbers of that, but at least it makes our work a bit easier. And in a linear algebra course and in my videos, you usually show that even though V star is so abstract, V and V star are isomorphic. So V is kind of isomorphic to V star in the finite dimensional case. But what I want to show you that in the infinite dimensional case, this is wrong. So I won't prove this, but I'll give you a suggestion why in the infinite dimensional case, V star is much bigger than V. And for today, to simplify our work, let's consider the space of continuous functions from -1 to 1. And I want to consider the following functional. So given f in V, consider the following functional, f hat in V star. And what this means is that f hat, again, nothing to do with Fourier transform, this is just the hat of today. It goes from V to R, and f hat of G, again, G is a function continuous function from -1 to 1, and f hat of G just takes the integral from -1 to 1 of f of x, g of x dx. And let me give you a little example. Suppose f of x equals to x cubed, g of x equals to x, then f hat of g, that's the integral from -1 to 1 of f of x times g of x, so x cubed times x dx, and that's the integral from -1 to 1 of x to the 4th dx, and you can calculate it to be 2/5. So just to show you, this is indeed for every f, it's a linear functional. It takes a function as the input and spits out a real number. And if you want, let me quickly show that f hat is linear, because f hat of, let's say, g plus ch, that's the integral, again, from -1 to 1 of f times g plus ch, again, dx, equals integral from -1 to 1 fg plus integral from -1 to 1 cfh. And that just becomes f hat of g. And this c comes out, and that equals plus c f hat of h. Yeah. Which is just what we wanted to show. We wanted to show that if you want t of x plus cy is tx plus cty, and that's why it is indeed linear and it's a functional. And not only that, the cool thing is this is kind of like a super functional, because now if you, not only for fixed f is this linear, but that transformation itself, it's linear. So consider now the following map from V to V star. It takes a function as its input and outputs f hat. And let's call this xi. So let xi go from V to V star. Xi of f equals to f hat. And actually what I want to show is that, well, first of all, xi is linear. Did I say psi? psi, sorry, or psi, anyway. I can't pronounce things anymore. So that this thing is linear. So in other words, suppose you have psi of f plus cg. Well, this is a functional, so this is f plus cg of hat, and apply it to a function h. That's f plus cg hat of h, which is just the integral from -1 to 1 of f plus cg h, which is the integral of fh plus c, the integral of gh. And that's precisely f hat of h plus c g hat of h, which is f hat plus c g hat of h, which is psi of f plus c psi of g of h. So you see, this thing, if you evaluate it at h, you get the same thing as this evaluated at h. So in terms of functions, they are actually equal. So psi of f plus cg equals to psi of f plus c psi of g. And in case you're wondering where's the analysis, don't worry, it comes. Don't worry. Right now you're happy. Afterwards you might be like, oh no, why did I ask that? So not only is psi linear, but actually we can show that it's an isomorphism. No, not an isomorphism. Very important. We can show that it's 1-to-1. It's not an isomorphism because actually I want to show this is bigger than that. So psi is 1-to-1. So suppose psi of f equals 0. So this means, I guess the 0 functional, and this means that f hat equals 0. And the 0 functional means that f hat of g equals to 0 for all g in V, which is the set of continuous functions. And in particular, this means that the integral from -1 to 1 of f of x, g of x dx equals to 0 for all g. But notice, this is true for all g, so just choose a very clever g to make this work. How about we let g equals f? Then what we get is the integral from -1 to 1 of f of x dx equals 0, which is just the integral from -1 to 1 of f of x squared dx equals 0. But look, if this non-negative function equals 0, the only way this works is if this inside is 0. You see, because if the function is positive somewhere, by continuity it's positive on like some neighborhood, and that would make the total integral positive. But this is not true, and I'm positive about that. So what we get is that f of x squared equals 0. So f of x equals 0 for all x. Again, continuous, so really for all x. And this just means that f is the 0 function. And that's exactly what we wanted to show. We assume psi of f equals 0, and we show that f is the 0 function. In particular, this is in injection. So this is a 1-to-1 map from V to V star. And whenever you have a 1-to-1 map from one space to the other one, this means this is bigger than this, or equal, so at least in size. So in particular, what we can conclude in this example is that the dimension of V star is greater or equal to the dimension of V. And what I want to show, and again, it's not a proof, because it's possible that there's some other bijection between those. What I want to show is actually this psi is not onto. So in some sense, V star is kind of bigger than V, because there is one function, there's one functional which cannot be expressed in this form, which is precisely called the Dirac Delta. So psi not onto. So again, we have V, we have V star, and we have psi that takes F and gives you F hat. And this is the space of all the hats. So all the functions which can be written as something hat. I want to show that there's one functional that cannot be written in this way, and I call this Dirac delta. So define, and here Dirac delta at 0. Dirac from V star to R. And what does Dirac delta do? So it takes, Dirac is in V star. And what does Dirac do? It takes a function as its input and evaluates it at 0. And this is the definition, not the physics one, the correct definition of the Dirac delta at 0. And if you want Dirac delta at x, just evaluate it at x. Okay? And I want to show that this thing cannot be written as something hat. So show. And by the way, it is a linear transformation because Dirac of f plus cg, that's f plus cg at 0, that's f of 0 plus cg at 0, and that's Dirac of f plus c Dirac of g. It is linear, so it is indeed a linear transformation. I'm not claiming anything about continuity, by the way, but at least for our purposes, it is in V star. And what I want to show that the Dirac is not in the range of psi. In other words, show that Dirac cannot be written as psi of f, which is f hat, for any f. Continuous. And we do this by contradiction, so suppose the Dirac delta is equal to f hat for some f. This is equality of functionals, so let's evaluate it at g. So then, for all g in continuous functions, Dirac of g equals to f hat of g. So in other words, g of 0 equals to the integral from -1 to 1 of f of x, g of x dx. And from this identity, we want to derive a contradiction. And remember, g is arbitrary, so we would like to choose a very nice g that makes this work. Okay, so we would like to show that f, basically our contradiction is we kind of want to show that f is 0. So suppose, and this is kind of weird, suppose f is not 0. In other words, suppose f of x is not 0 for some x. And moreover, you'll see in a second why. Let's assume this x is non-zero as well. And then we'll see what happens with the case x equals 0. And in particular, if this is non-zero, it's either positive or negative. So without loss of generality, assume f of x is positive. Okay. And again, the reason is if you assume it's negative, just repeat the same proof and you get a similar contradiction. So we basically have some x where f is positive. Here f of x is positive. In particular, so far, we haven't used continuity yet. Now, because f is continuous, and here is where the analysis comes in, finally. Because f is continuous, well, it means that f also has to be positive on some neighborhood. On, let's say, an interval of the form x minus epsilon and x plus epsilon for some epsilon positive. So I'm not using delta because I'm already using delta for Dirac delta. And in particular, on some neighborhood we can assume f is positive. And also, by the way, you see x is non-zero, so it has some distance away from 0. And if you want without loss of generality, but not really, you can assume the same thing. We can assume x is positive. In particular, if x is positive, by choosing epsilon so small, we can actually assume that this and 0 are disjoint. So assume that if you want x minus epsilon, x plus epsilon is disjoint from the set 0. And we'll need this in a second to construct our function g. So we do know that f is positive on this little piece. And look, how do we construct g? Simply as follows. X minus epsilon, x plus epsilon, and let's say this is 0. G is simply any continuous function you want, not even differentiable. So just think of a piecewise linear function that is positive here, and then 0 everywhere else. In particular, it's 0 at 0. So let g be any continuous function. In continuous on minus 1, 1. Be such that so g is positive on our interval x minus epsilon, x plus epsilon, and g is identically equal to 0 elsewhere. And by the way, so yeah, you could have the endpoints minus 1 and 1 to be a problem, but not really. If f is positive, let's say at minus 1, it's also positive nearby. So just choose that nearby point and it wouldn't really affect our proof. So, or easier, just consider the open interval or something, maybe that would make it easier. So in particular, so g is any positive function, any continuous function that's positive here and 0 everywhere else. If you want, just construct it in terms of linear functions, that's fine, or some parabola, whichever you like. And in particular, we would like to choose this function g to get a contradiction. Because remember what we had. Because we then have g of 0 equals to the integral from minus 1 to 1, f of x, g of x dx. But look, we assume that this interval is far away from 0. In particular, it is true that g of 0 is 0. Okay. So on the one hand, this is 0. On the other hand, what do we know? We know that f is positive on this interval. Okay. So f maybe looks something like that. So in particular, f is positive on that interval, and remember, g is 0 outside of that interval. So outside of the interval, you're just multiplying f by 0. So really the only part of the integral that matters is the integral from x minus epsilon and x plus epsilon. And I guess I'm abusing notation, but let's say f of t, g of t dt. And that just becomes, so f of t, g of t dt. Okay. And look, here's the thing. F is positive on that interval, and by definition, g is also positive on that interval. And epsilon is a fixed number. We're not taking any limits. So this whole thing is positive. So what you get then is that 0 is strictly greater than 0, and that's a contradiction. So what does that tell us? Well, it tells us that f, it cannot be positive anywhere, and it also cannot be negative anywhere by the same argument. So what this means is that f is identically equal to 0, except maybe at x equals 0 and the endpoints minus 1. But, and again, let's ignore the endpoints, whatever. But look, f is a continuous function. So if it's 0 everywhere, except for maybe a point, by continuity it forces the point to also be 0. So if f was non-zero at 0, then this function wouldn't be continuous. So in fact, we do get that f is identically equal to 0, but then what does that tell us? It tells us that the Dirac delta is just 0 hat, but 0 hat is like integral of 0 times g, and that's just the 0 functional. But the problem is the Dirac delta, it's not the 0 functional. For example, I don't know, take Dirac delta of the function, I wanted to say x, but that wouldn't work, but let's say x plus 1, you evaluate x plus 1 at 0, so you get 1. In particular, the Dirac delta is not identically equal to the 0 function. And that's where we get a contradiction. So what this is saying is that the Dirac delta, it cannot be of the form f hat. And what's more interesting is figuring out what's happening here. Because what did we really say? We say if the Dirac delta is of the form f hat, if delta equals to f hat, what does f hat do? Other than 0, it's just 0. But basically at 0, it could be anything it wants. And usually when you require the integral to be 1, what this means is that the Dirac delta, it's 0 everywhere, but with an infinite spike at 0. And in fact, this is true when you see like pictures of the Dirac delta functional. So usually it looks something like that. That's the Dirac delta at 0, where it's 0 everywhere, but a spike, infinite spike at 0. And at least what we have shown is that, well, it has to be 0 everywhere other than 0. So it does make sense. And in particular, so the Dirac delta isn't a function, so it's not of the form something hat, but it's what's called a functional or a distribution. And there's this whole thing called distribution theory that studies stuff like the Dirac delta. And there's some pretty neat things about it. And in fact, I did something on like weak derivatives, how to differentiate a non-differentiable function that deals a bit with those distributions. All right, so I hope you like this linear algebra and analysis extravaganza, kaboom. I hope you like this, and if you want to see more math, please make sure to subscribe to my channel. Thank you.